my KCET 2026 aspirants, so welcome to Sankalp batch 2026, and in today's class we are going to start the chapter 2 of chemistry, that is electrochemistry. Okay, so I'll be talking about this chapter. Generally students find little bit difficult. Why? Because it has some formulas, okay, some complicated things are there, but if you have done my bridge course correctly on physical chemistry, this chapter you will understand the basics. Okay, so in this part we'll be talking about we'll start from the basics. I'll go very detailed, and I have tried to make the PPT little bit colorful and attractive so that you don't feel bored during the classes. Okay, so students, I want all of you to sit with a notebook and a pen and note down all the important things that I'll be discussing in today's class. Okay, fine. So today's chapter, as you all know, this is electrochemistry, and yes, so how many parts we have for this particular chapter? So in today's class we'll be doing part 1. Okay, so basically I have 4 parts, but in today's class we will be talking about part 1. And what all things we have in part 1? We have first of all introduction, a very brief introduction about what we'll be studying today. Next we have electrochemical cells, we'll talk about that, and third we'll talk about galvanic cell. Okay, so this is on part 1 today. Next, on part 2, what all things we have? Nernst equation and conductance of electrolytic solution. Then in part 3, okay, so in part 3 basically we'll be talking about electrolytic cells and electrolysis, and in part 4, the final part, we have batteries, fuel cells and corrosion. Okay, so these are the topics that we have in 4 parts. There will be 4 lectures in this class, in this chapter, and today's is the first part. Okay, fine. So first let's go to the introduction of this chapter. So can you see this diagram? What do you think? There are 2 arrow marks, there is a test tube, some chemical reaction is going on, and there is a bulb glowing that. Can you just quickly comment down what can you think in this particular diagram? What, suppose this diagram is given to you and is asked to describe or to think something around it, what will be your thoughts? Please write down in your rough notebook or put down in the comment section quickly. So basically what happens is, we know that there are different forms of energy. There are n numbers of energy. You have nuclear energy, wind energy, solar energy, you have tidal energy, you have light energy, you have sound energy, you have electrical energy, you have chemical energy, you have so many energies, potential, kinetic, right? There are vibration, rotational, there are thousands of energy. But there is one law in this nature which says that energy is conserved. You cannot produce more energy or less energy. The energy can only be transformed from one form to another form. Right? The energy can only be converted from one form to another form. So today's class, or in this chapter, we will be dealing with 2 important energy forms. What is that? Electrical energy and chemical energy. Okay, electrical energy and chemical energy. Okay, so we'll be talking about 2 different energies, that is electrical energy and chemical energy. Now, how this chemical energy is produced? By chemical reactions. When the chemical reactions happen, chemical energy is produced. Now, this chemical energy can be converted to electrical energy. Okay, I hope you are getting this one. So let me just draw here. Yeah, so we have chemical energy. Okay, I have chemical energy here, and this chemical energy, from where do we get this chemical energy? From chemical reactions. Right? Chemical energy will get from chemical reactions. Then this chemical energy can be converted or can be changed or exchanged with which type of energy? Electrical energy. Okay, clear? So now what happens here is, if you see, chemical reactions takes place, it gives you chemical energy, and that chemical energy can be converted to electrical energy. If electrical energy is there, that can be converted to chemical energy, and as a result of which chemical reactions will occur. So these 2 energy, chemical to electrical energy to chemical energy, is what we are going to study in this particular chapter, and I hope that is clear to all of you. Okay, so Electrochemistry. So this line I have taken from your NCERT book. To understand what is electrochemistry, you should know that, see, electrochemistry is the study of production of electricity from energy released during the spontaneous chemical reactions. This is one important word here, from spontaneous chemical reactions. So when I say you that, see, when I say you that this chemical energy has come from chemical reactions, has come from chemical reactions. What type of chemical reactions it is? It is spontaneous chemical reactions. Now, I hope all of you remember what is spontaneous chemical reactions. Those reactions which can occur by its own, okay, which does not need any type of extra initiation, okay. So the reactions will happen by itself, they will produce this chemical energy will convert to electrical energy, or else what will happen? Electrical energy will give you chemical energy, and through this chemical energy we can conduct some non-spontaneous chemical reactions, okay. So electrochemistry is the study of production of electricity from the energy released during the spontaneous chemical reactions. How much chemical reactions has happened, how much chemical energy is produced, how much electrical energy can be converted from this chemical energy, and the use of this electrical energy to bring about non-spontaneous chemical transformations, okay. So you can use chemical energy to electrical energy to chemical energy, okay. Now when you are giving this electrical energy, chemical energy is produced and that will be driving certain chemical reactions. These chemical reactions are non-spontaneous, okay, fine. Let's now move to the second topic, that is electrochemical cells. Now we discussed that this chapter is about 2 energy and their interconversion, right, but there should be some device that will do this interconversion, right. So there should be one device in which if you put chemical energy it will give you electrical energy. There should be one device, if you give electrical energy it will give you chemical energy. That conversion can happen through the device, and these devices are called as electrochemical cells. I hope what is electrochemical cells is clear. These are the devices that convert chemical energy into electrical energy or vice versa, okay. So what are these types of electrocentres? We have 2 types, definitely we will have 2 types. One will convert chemical to electrical, another will convert electrical to chemical, right. So there are 2 types of electrochemical cells. The first one is your galvanic cell and the second one is your electrolytic cell, okay. So what is the role of galvanic cell? Galvanic cell converts chemical energy to electrical energy, okay. It converts chemical energy to electrical energy. So just imagine like this, we have something here, you gave chemical energy, okay, and it gave you electrical energy. Then what is this device? This is galvanic cell. I hope this is clear, you got it. Now in this galvanic cell we generally have 2 chambers, okay. When we talk about the construction and all, it will be more clear. We have 2 chambers in that, okay. Next, redox reactions. What is this redox reaction? So chemical energy will come from where? From chemical reactions, right. What type of chemical reactions? Spontaneous chemical reactions. What type of spontaneous chemical reactions we'll be studying? Redox reactions, okay. So redox reactions will take place, or the chemical reaction that will take place will be redox reactions. These redox reactions will give you chemical energy, and that chemical energy will be converted to electrical energy by using galvanic cell, okay. Now the opposite of that is your electrolytic cell. In electrolytic cell what will happen? Electrical energy will be converted to chemical energy. This chemical energy will do some reactions, the non-spontaneous reactions. Next, here we have only 1 chamber, okay. This, when I talk about the construction, you will be more clear. It is used to purify the metal, so its application we'll see in detail. So for now we have understood what is the device called as which converts electrical to chemical or chemical to electrical, that is your electrochemical cells. Next we have galvanic cell which converts chemical to electrical, and we have electrolytic cells which converts electrical to chemical, okay. Fine. Next we'll move to galvanic cell. Okay, so galvanic cell, as we all have seen, it converts the chemical energy to electrical energy, right? This we have learnt, this we have understood. Now under galvanic cell there are so many things that we will be talking about. First one is your Daniell cell, electrode potential, cell potential, measurement of electrode potential, and inert electrodes. So these are the 5 topics that we have under galvanic cell. Okay, so first let us see. So when you have the, as you all know, it converts this chemical energy to electrical energy. So what type of, so I told you in the previous that there will be 2 chambers. So you see, this is an example of galvanic cell. It has 2 chambers or 2 containers. So that is what we were talking about. What are these 2 chambers? What is this salt bridge? Everything will be explaining in detail. Okay. Now see, the energy of the spontaneous redox reaction is converted into electrical work or electrical energy, which may be used for running a motor, electrical gadgets like heater, fan, geysers, etc. So once these chemical reactions happen, we will get the electrical energy, which will be used for different purposes, like you can use it for heater, fan, geyser, etc. Fine. So now we will talk about Daniell cell. Now galvanic cell, or I can say Daniell cell, is an example of galvanic cell, or it is a type of galvanic cell. Okay, so you will understand what I am saying after some time. Just let's first understand this Daniell cell. So here you can see we have 2 chambers. Okay, we have 1 chamber here and 1 chamber here. Okay, now what happens is, in this you have zinc and copper are taken as electrode. We have 1 zinc electrode and I have 1 copper electrode, right? And there are 2 chambers. I have zinc electrode and copper electrode. Okay, there will be chemical reactions here. The potential that is generated, or the electricity, the voltage that is generated here is 1.1 volt. Okay, and we'll talk about how it is coming in all detail. So what basically you see here, we have 2 containers. In 1 container I have an electrode, and you can also see a electrolyte here, right? We have a electrode, a electrolyte. On the other side also I have an electrode and an electrolyte. Okay, now what happens here is, the reaction between them, Zn plus Cu2 plus gives you Zn2 plus Cu. Okay, then you have reduction half cell, oxidation half cell. All these reactions are given. We'll talk about it in some time. Okay, just now see this one. So what now, see, each half cell, this one part is called as half cell. Okay, each half cell consists of a metallic electrode dipped in an electrolyte. As you can see, Zn and ZnSO4. The 2 half cells are connected by a metallic wire through a voltmeter and a switch externally. So these are connected by wires and a switch externally. The electrolytes of the 2 halves are connected through a salt bridge. So I'll draw the salt bridge here. So a salt bridge is like this, which is present between 2 electrolytes. Okay, this is the salt bridge. Now what happens? Let's understand the mechanism of this. Now see, zinc is something which can oxidize easily. Okay, zinc can undergo oxidation. So what will happen? Zinc. Oxidation means what? If you remember, oxidation is loss of electrons. So what does zinc do? Zinc loses 2 electrons. If it loses 2 electrons, what will be the charge on zinc? It becomes Zn2 plus. Okay, now so this zinc, you can see here, the zinc metal comes out of the electrode as Zn2 plus, because it is now iron, right? Once it is forming iron, it comes out of the metal as Zn2 plus, and there are electrons left on this rod. Which is these electrons? These 2 electrons that is produced. Now what happens? These electrons, 2 electrons, move from here to here. Okay, now in the solution we have copper sulfate. So at this side what happens? This is on the left hand side. Now what happens on the right hand side? Right hand side, this copper 2 plus, okay, it takes 2 electrons. These 2 electrons are coming here, right? It takes both of the electrons and you get copper. right? So this is a reaction happening. Which type of reaction is happening? One is undergoing oxidation, another is undergoing reduction. So this is definitely oxidation and this is reduction, right? When one undergoes oxidation, one undergoes reduction, it is called a redox reaction. So here a redox reaction is happening. Due to this redox reaction, what happens? There is the movement of electrons. Now if you remember, movement of electrons is called as current, right? So now what, when the electrons are moving, current will also flow in opposite direction. So now you can see how this redox reaction has led to the flow of electrons, and the flow of electrons has led to the formation or the flow of current. Right? So now you can take any combination. You can take silver and copper, you can take zinc and silver, you can take like for example mercury and copper, right? Different combinations are possible. So this particular combination, zinc and copper, okay, this particular combination zinc and copper is called as your Daniell cell. Okay, and here this Zn2 plus is taken as 1 molar and copper sulfate is, sorry, ZnSO4 is taken as 1 molar, copper sulfate is taken as 1 molar. Okay, so that is the thing, that is Daniell cell is a type of galvanic cell. In galvanic cell we will have two particular chambers, one will undergo oxidation, another will undergo reduction. When the one undergoing oxidation leaves electrons on the electrode, that electrons flow here, and this side these ions present in the solution takes that and it becomes reduction. The process occurring here is reduction. Now when I have oxidation and reduction simultaneously, I call it as redox reaction. Now if I have this particular combination of zinc and copper, then only we will call it as Daniell cell. Any other combination we will call as galvanic cell. So I have a conclusion here that Daniell cell is, all Daniell cell is a galvanic cell, but all galvanic cell is not Daniell cell, right? That is very clear here. One more thing you should remember, the concentration of ZnSO4 and the concentration of copper sulfate should be 1 molar. Clear this one? I hope this is very clear to all of you. Okay. Next we'll talk about electrode potential. What is this electrode potential? Okay. Now see here, in this suppose I have taken, in this container you have taken Zn sulfate, ZnSO4 and Zn rod, right? So now what will happen, as we have seen that zinc is giving Zn2 plus and electrons are present on this. So you see that there is a charge difference. What you can see, the electrons, this rod is negatively charged and Zn2 plus, the outside, is positively charged. So there is a charge difference between the electrode and the electrolyte. This solution is called as what? Electrolyte. Okay, this is called as electrode, right? So there is a charge difference. This is negatively charged, this solution is positively charged. So here between, when this junction is there, this boundary, there is a charge difference, there is a negative and a positive charge difference is there, and that potential difference, whenever we have a charge difference, we call it as a potential difference. So this potential difference is called as your electrode potential. Okay, this potential difference is called as electrode potential. Now if you see on the side of copper, now what happens, copper, these electrons were coming here, right, and copper 2 plus is absorbing that, this copper 2 plus is taking these electrons. So the rod is becoming positively charged and you have sulfate ions in the solution. So this rod is positively charged and sulfate ions are there in the negatively side outside. So that happens, this creates again a charge difference is there, due to which we have a potential difference here also. This is called also electrode potential, right? So let's see here, Okay, the potential difference developed between the electrode and the electrolyte is called as your electrode potential. You can see here, if metal is there, it comes out as M plus, leaves the electron, and there is a potential difference here which is called as your electrode potential. Let's see this in little bit detail. Okay, yeah, you can see here, at each electrode electrolyte interface, interface means between one electrode and electrolyte, there is a tendency of the metal ions from the solution to deposit on the metal electrode, trying to make it positively charged. So there can be two things. You can have, see, you can have, suppose this is there, let me take black color, yeah. So you can have that the solution is having negative charge and the rod is having positive charge. This type is possible. Or you can have the rod is having negative charge and solution is having positive charge, right? So both type of potential is possible. So now there is a possibility that the metal ions from the solution deposit on the metal electrode, trying to make it positive. So if you have seen the copper side, what does the copper is doing? Copper is depositing on the metal rod, right? When you see Cu2 plus 2 electron gives you copper, this copper is solid. So copper 2 plus goes towards this electrode, takes this electron and gets deposited there. Now it is absorbing all the electrons of this metal, right? So that means this rod is become positively charged. Okay, electrons are coming, but copper is taking all the electrons, and that is why it becomes positively charged. So now you can see here, at the same time, so one possibility is there where they are making the electrode positively charged, or the right hand side part. At the same time, the metal ions, metal atoms of the electrode have a tendency to go into the solution as ions and leave behind the electrons at the electrode, trying to make it negatively charged. Is it happening there? You can see here, the metal comes out as metal ions and you are leaving electrons on the rod, making it negatively charged, right? So what happens? At equilibrium, there is a separation of charges, and depending on the tendencies of the two opposing reactions, the electrode may be positively or negatively charged with respect to the solution. So I can say that in particular this example, this electrode is negatively charged, right? This electrode is negatively charged and this electrode is positively charged. Okay, clear? So why this electrode is negatively charged? Because here we have this ions are coming out, they are giving electrons to this electrode, and that is why it is getting negatively charged. Here what happens, these ions are taking these electrons from the metals and making it positively charged, right? So that is what we have seen here. Now what happens? What happens is, so this side, one side is, so when the concentration of all the species involved in a half cell is unity, then the electrode potential is known as standard electrode potential. Okay, then the electrode is called as standard electrode potential. What is the standard electrode potential? What is the standard electrode potential? Now see, suppose you have measured, okay, if this concentration is 1 molar and this concentration is 1 molar, then whatever potential is developed between this electrode and this electrolyte, that is called as standard electrode potential. Okay, so that is what, according to IUPAC, standard reduction potentials are now called the standard electrode potential. So now definitely we have two types of potential. If you see, I have two chambers, right? I have two chambers, okay? On one second, yes, this is Zn side, or I can say the left side, okay? Here what is happening? Zn is coming out as Zn2 plus. There are electrons left on the rod. Okay, there is a negative and positive surface is there. So what is this Zn undergoing? Zn2 plus, Zn is getting converted to Zn2 plus, leaving electrons. Zn is getting converted to Zn2 plus, leaving 2 electrons. What is this container undergoing? Oxidation. Okay, So if it is undergoing oxidation, then we will call it as oxidation potential. This half cell will be having oxidation potential, or the electrode potential here is called as oxidation potential. On the other hand, when you have copper rod, you have copper rod Cu2 plus, okay, they come here, take the electrons and get deposited as copper. Okay, so what happens here? Okay, Cu2 plus 2 electrons gives you copper solid, that is there. Now what happens? This is the right hand side. Okay, this is the right hand side, and here what happens? Reduction is taking place, and this electrode potential is called as reduction potential. Reduction potential. Okay, so we understood what is electrode potential. Electrode potential means the potential difference between the electrode and the electrolyte. So if that electrode is undergoing reduction, we will call it as reduction potential. If that electrode is undergoing oxidation, we will call it as oxidation potential, right? So every electrode can either be an oxidation potential or can have a reduction potential. But IUPAC told that let's for a convention, for a commonality, or for a easy thing, let's just talk about reduction potential of all the metals. Even though metal undergoes oxidation, we will talk about it, or we will represent it in the form of reduction potential. Now how does that happen? For example, this potential between copper, okay, copper is undergoing reduction, so this potential difference is 0.34 volt, okay, and this zinc oxidation potential is minus 0.76 volt, okay, that is the oxidation potential. So I can write E oxidation of zinc is how much? Minus 0.76. But what did IUPAC told me? To represent everything in the form of reduction potential. So what I will write? E reduction of zinc, okay, that is now the sign will change. Okay, so how to convert oxidation potential to reduction potential to oxidation potential? Just you have to change the sign. Okay, so if I want to write the reduction potential of copper, since it is undergoing reduction only, so E reduction of copper will be how much? 0.34. Okay, and if I want to write its oxidation potential, which is not required, it will become minus 0.34 volt. But we don't need oxidation potential because IUPAC wants everything to be in the form of reduction potential. Okay, now what does this 0 denotes? Just now we talk about if the solution concentration is 1 molar, then this electrode potential is told as standard electrode potential, and to represent standard electrode potential we use the not symbol. Okay, standard reduction potential, we'll talk about it after some time. Okay, so according to the IUPAC convention, standard reduction potentials are now called as standard electrode potentials. Now in a galvanic cell, the half cell in which oxidation takes place is called anode, and it has a negative potential. Okay, where oxidation takes place, on the left hand side, right, where oxidation takes place, that is called as anode. Okay, this is important. Where oxidation takes place, that is called as anode, and it has a negative potential with respect to the solution. Okay, that will have a negative value. The other half in which the reduction takes place is called as cathode, and it has a positive potential. Okay, so generally it is found that what we find generally, we find here, yes. So what happens? Where oxidation takes place, that is called as anode, and it has a negative potential. Where we have reduction, that is called as cathode, and it has a positive potential. Okay, you can see the values I just showed you. Zinc will have minus 0.76 oxidation potential, copper will have an reduction potential of plus 0.34 volt. Now thus there exists a potential difference between the two electrodes, and now see, we have two types of potential difference here. This is very important. If I construct this one, see, this is my galvanic cell, so easy to draw, right? I can just draw in 1 minute. Salt bridge is there, which I am ignoring for now. What is this rod? this is zinc rod. What is this solution? This is zinc sulfate. I have here copper rod, and here it is copper sulfate. Okay, now what happens? Zinc sulfate, copper sulfate, zinc sulfate, copper sulfate is there. Now I told you that there is a electrode potential between this zinc rod and zinc sulfate solution, right? There is a interface here. There is an electrode potential here whose value I told you is minus 0.76 volt. Now there is a electrode potential here also between this copper and this electrode, between this copper sulfate electrolyte and this one we have, that is 0 plus 0.34 volt. Now you can see that there is a potential difference between these two chambers. One potential difference is inside the chamber between the electrode and the electrolyte. That is oxidation potential here, reduction potential here. Potential difference between this electrode and this electrolyte, potential difference between this electrode and this electrolyte. There is a potential difference within the chamber, here there is a potential difference within the chamber. Now if you see from outside, there is a potential difference here and there is a potential difference here, right? Now what happens when you connect this series, electrons will start flowing. Okay, so you can see this is lower potential, this is higher potential. From here to here, the electrons will start flowing. Okay, so that when this potential difference between two electrodes is called as your EMF. Okay, we'll see that now. So you can see there exists a potential difference between the two electrodes, and as soon as the switch is in the on position or when the circuit is connected, the electrons flow from the negative electrode to the positive electrode. So negative anode to cathode, the electrons will start flowing. Okay, and the direction of the current is opposite to that of the flow of electrons. So if I show that diagram to you once again, you can see that yes. If I see that, now this is electrode, the electrons will start moving from here to here. Okay, electrons are moving from negative potential to positive potential, and current direction will be in the opposite direction, right? Okay, so what we were discussing, yes, this is what we have understood till now. So what all things we have understood till now, let's quickly summarize. We have two types of cell. One is galvanic cell and one is electrolytic cell. Galvanic cell converts chemical energy to electrical energy. In galvanic cell there are two chambers. One side there is oxidation, one side there is reduction. Oxidation part is negative and is called as anode. There electrons are generated. These electrons move outside the circuit towards the right hand side. Their reduction takes place. The potential difference between the electrode and electrolyte on the left hand side is called as oxidation potential. The potential difference between the electrode and the electrolyte on the right hand side is called as reduction potential, right? I hope you are getting this one. Okay. Now the question arises, can you measure the potential individually? Means I told you here that this value, okay, this zinc and ZnSO4, I told you that this potential difference here is minus 0.76 volt. But how did I know this? Can I just measure? There is some instrument present here that I can measure directly, or there is some other technique to that? We will answer this question towards the end of this lecture. Okay, so now the question you keep thinking, and what do you think? Do comment down whether yes or no. Can we measure? Suppose I want this electrode potential between zinc and the zinc sulfate solution minus 0.76 volt. How can I find that? Okay, can I measure it directly, or I have some I can say process for that or something that I can use? Comment it right now if you know, or wait for the end of the lecture to know this. Okay, till now everything is clear. Okay, we are still talking about galvanic cell. There is a electrode potential in this chamber, there is a electrode potential in this chamber. From outside if I see, there is a potential difference between these two. So the electrons start moving from the negative to positive. And when, so you can see because of this chemical reactions, here there is a oxidation reaction, here there is a reduction reaction. Because of this chemical reaction, electrode potentials are generated. Because of these electrode potentials, the electrons are flowing. Okay. Clear to everyone? Okay, dear children, let's move to the next thing. So as I told you, what is cell potential? We have electrode potential difference here, we have electrode potential difference here due to these electrons start flowing. The difference between these two electrode potentials is called as your cell potential. Okay, the difference between electrode and electrolyte is called as electrode potential. The difference between electrode and electrolyte, oxidation, reduction potential, oxidation potential. But the difference between these two potentials is called as your cell potential. So let's see here the potential difference. Okay, the potential difference between the two electrodes of a galvanic cell. Okay, potential difference between two electrodes of a galvanic cell is called as cell potential. Okay, and what is the unit of this cell potential? It is measured in volts, or the unit of this is volts. Next, what we have? Okay, the cell potential is the difference between the electrode potential, the reduction potential of the cathode and the anode. Okay, reduction potential of cathode and anode, that is the formula. So we have the cell potential formula, that is E right. Cathode is on the right hand side and anode is on the left hand side. So reduction potential of cathode minus the reduction potential of anode. Okay, so this is important. It is called the cell electromotive force, okay, of the cell when no current is drawn through the cell. Now when the switch is off, okay, when this switch is off, still there is a potential difference between them. Okay, that is called as cell electromotive force. Okay, that is when you have no current is there, okay, only you have the circuit is not closed, you have a potential difference between two sides, that is called as cell electromotive force. Now anode is on the left and cathode is on the right, we know that. The EMF of the cell is positive and is given by the potential of the half cell on the right hand side minus half cell of the left hand side. So you have understood what is the difference between cell electromotive force and cell potential. When the current is on, the potential difference between two is called as your cell potential. When the current is not there, when the switch is off, the potential difference between two is called as cell electromotive force. Okay, so now I will give you a very interesting trick to remember this left and right. Ma'am, what is this? We are getting confused with left and right. Don't worry, write down this one, lone. Okay, write this number or name lone, L-O-A-N, lone. Okay, not lone, lone, L-O-A-N. What is this? See, yes, L stands for left. Okay, left, L stands for left. O stands for oxidation. Okay, A stands for anode. N stands for negative. Okay, so what is this? Left side. See, left side is always oxidation. Left side always oxidation will take place. That electrode will be negative in charge. Okay, that will be called as anode and it is negative in charge. Okay, so anode definition is what now? Anode is where it is negatively charged? No. Anode is where oxidation takes place. Cathode is where reduction takes place. Okay, in the lower classes we have studied that anode is positive, cathode is negative. That happens, but that is in electrolytic cell. In galvanic cell what happens? Anode is negative and cathode is positive. So it is always, whenever it is asked what is anode, what is cathode, you have to say anode is where oxidation takes place. What is anode? Anode is where oxidation takes place. Okay, and what is cathode? Cathode is where reduction takes place. Okay, anode is where oxidation takes place and cathode is where reduction takes place. Okay, now what is the cell potential here? The reduction potential minus the reduction potential of cathode minus the reduction potential of anode. Okay, so E right minus E left. Okay, so always remember what we have. We have anode is on the left side. Okay, just a minute. Yeah, so we have anode on the left side. Okay, and we have cathode on the right side. Next, what we have? The EMF of the cell is positive. Okay, the EMF of the cell is positive and is given by the potential of half cell on the right hand side minus the potential of the half cell on the left hand side. Okay, E right minus E left. Okay, now how to write this cell notation? What is cell notation? Ma'am, do we have to always write these type of diagrams, big diagrams we have to do? No ma'am. For cell potential means it is a way, to represent cell. It is a way to represent cell. Okay ma'am, I know what is cell notation. It is a way to represent the cell. Then how do we do that? How do we represent that? So first of all, start from the left hand side. Okay, what is here? I will draw the salt bridge which is missing here. Okay, let me just add here. Okay, so this we don't have to consider. Okay, so salt bridge. Okay, so now we have start from the left center. What is this on the left hand side? Zinc rod is there. So let us write down zinc rod. Okay, what is the physical state? Is it solid, liquid, gas? Solid state. So let us write down solid. Now when this is solid, and then what is this? Zinc in contact with zinc sulfate, right? What is the Zn component here? Zn2 plus, and it is in aqueous media. So I will have when there is a phase change, put a single line, and then in the solution I have Zn2 plus, which is aqueous solution, right? Zn2 plus. Now this Zn2 plus solution is in contact with what? Is in contact with the salt bridge, right? So we will have a salt bridge here. Salt bridge is represented with a double bond. Next, this salt bridge is in contact with what? This ion, which is copper 2 plus. Copper 2 plus is in aqueous solution. So you will mention copper 2 plus aqueous. Next, this is in contact with the copper electrode, which is again in the solid state, right? So that is how is the cell notation. Start from the left hand side. Zinc rod, zinc electrolyte, salt bridge, copper electrolyte, copper rod. Okay, and what happens in this, the concentration is also mentioned. Okay, for this one and this one, because these are electrolytes, their concentration will also be mentioned. For now we have considered it as 1 molar, so I will write 1 molar. Clear? Okay, so you have understood now everything. Now let's try to solve a question. Okay, what you have been given? You have been given with a cell of, now this side I have taken copper or Ag plus. You have taken copper on the left hand side and silver on the right hand side. There is a salt bridge. Okay, 1 molar copper nitrate is there, the electrolyte, and 1 molar silver nitrate electrolyte is there. Now tell me whether it is a galvanic cell or Daniell cell. If you have understood, put down in the comment section whether it is a galvanic cell or a Daniell cell. If you are watching this video, write down now itself in the comment section. Okay, so what all things we have to do for this question? You have to write the half cell reaction. What is half cell? You have to write the reaction happening on the left hand side and the reaction happening on the right hand side. The left hand reaction is oxidation, right hand reaction is reduction, right? So we have to write the oxidation reaction, and this is the anode reaction, this is the cathode reaction. Remember lone? So I will write what happens at anode. So I will write at anode. Just a minute. Yeah, at anode. At anode, what is happening? Oxidation is happening. Whose oxidation is happening? Copper is undergoing oxidation. You see in the previous combination, copper was on the reduction side, but here copper is on the oxidation side. So copper is undergoing oxidation. Just a minute. So let's see the next question. We have a cell reaction where I have, you can see that on the left hand side copper is there, on the right hand side silver is there. But you can also see that here we have, sorry, one second. Yes, you can see that copper oxidation is changing from Cu to Cu2 plus. So that means what can I say? That copper is undergoing oxidation, right? Copper is undergoing oxidation, and silver you can see Ag plus 2 Ag, right? Ag plus 2 Ag. That means silver is undergoing reduction, right? Silver is undergoing reduction, copper is undergoing oxidation. So what to do next? Now we have to write the half cell reaction. So we have to write the reaction of copper and we have to write the reaction of oxidation, reduction. Now oxidation, I just taught you lone. Oxidation will take at what place? At anode. So this reaction will definitely take place anode, and this reaction will take place at cathode, right? Now let's write down the reactions. So what is the reaction at anode? At anode, okay, at anode, copper is undergoing oxidation. Cu will get converted to Cu2 plus 2 electrons. Okay. At cathode, what is happening? Reduction. Whose reduction? Silver reduction. So you have Ag plus 1 electron giving you Ag. Okay. So I got half cell equations at anode reaction and at cathode reaction. Next task is to write the cell notation. I taught you how to write the cell notation just now. We'll start from the left hand side. So what is here? Copper anode is there. So I have copper rod here. Then it is in the solid state. Then I have there's a phase change. You have to put a single arrow here. Then you have to put copper 2 plus in the aqueous phase. Okay, copper 2 plus in the aqueous phase. Next what I have, this is in contact with the salt bridge. So for salt bridge we'll put a double bond. Next, here the copper 2 plus concentration is given 1 molar. You also have to mention 1 molar here, okay, comma 1 molar. Then you have here Ag plus, okay. So I have Ag plus, in bracket I will write aqueous, comma 1 molar. That is also 1 molar given here. Then you have silver electrode, so one solid line, Ag solid. Okay, so this is my cell notation. Then what is E of the cell? E of the cell is what? Right minus left, right? So I can write E of the cell will be equal to E on the right, what is there? Silver is there, or reduction potential of silver. So reduction potential of silver minus the reduction potential of copper. Now since this is 1 molar, I can say that these are also standard reduction potential. So here you can put E0 and E0. Okay, right, it is always right minus left or cathode minus anode. So cathode minus anode. You can see I have written the reduction potentials. Clear? Okay. So now the question is arising, can we measure the electrode potential individually? I asked you this question before also. This, suppose I want copper electrode potential is 0.34. So can I just take copper rod and the copper electrolyte and I'll put a machine and that will tell me the electrode potential between both of them? No. No. We can measure only the difference between the two half cell potentials that gives the EMF of the cell. Means always what we do or what we have to do is, you always have to take a combination of two. Okay, suppose I want to take suppose I want to measure the copper electrode potential, I have to take copper definitely, but I cannot measure it individually. This side I have to put something. Okay, I have to put something and the difference between these two will be the given measurement, or the potential difference between these two can be measured. But I want only for copper. Then what to do? The solution for this is using a standard hydrogen electrode. Now a new member comes to the story, that is standard hydrogen electrode. Now what is this standard hydrogen electrode? See, standard hydrogen electrode, its electrode potential is considered to be 0 at all temperatures. Okay, the standard hydrogen potential is considered to be 0. Now I think many of you can understand. Just a minute. Now see, suppose I want to measure the standard the electrode potential of copper. Okay, so what I can do is, you take copper on one side. Okay, I'll show you that also. You take copper on one side, okay, and you take this hydrogen electrode, okay, which is called a standard hydrogen electrode, and its electrode potential is assumed to be 0. Now suppose this is x, okay, I want to find this x value. So what will this give me? This will give me the value of right minus left, okay, or 0 minus x. So this value suppose came to be 0.34. Okay, minus 0.34 something came, and that is what? 0 minus x value. So can I get the x value from here, that is 0.34? Okay, so in this way we can measure that. It is always the difference, but if I take standard hydrogen electrode, it is used as a reference electrode. Okay, this is a reference electrode, it is 0. So this difference will come something, that difference is taken as the value of the electrode potential of the another component. Okay, so Standard electrode potential I have already discussed. When the concentration is 1 molar, we call it standard electrode potential, and it is represented as E naught of the cell. Okay, so now let's talk more about standard hydrogen electrode, how it is constructed, or what is its construction. So standard hydrogen electrode is having one platinum electrode coated with platinum black. Okay, you have this platinum electrode. Okay, it is a platinum electrode and it is coated with platinum black. Okay, now what happens here? When the electrode is dipped in an acidic solution and pure hydrogen gas is bubbled through it. So this is an acidic hydrogen, okay, acidic solution of hydrogen, and you have pure hydrogen gas bubbled to this one, okay, to this tube. Next, what happens? The pressure of the hydrogen gas is 1 bar and the concentration is 1 molar. So here one reaction happens. What is that reaction? So what happens? This H plus, the H plus present in the solution gains 1 electron and gets converted to half H2. Okay, so this is a reduction reaction happening here. The potential of this particular reaction or this particular electrode, E naught value of H plus to H2, is considered as 0. Okay, clear? Fine. Next we'll talk about application. So you have to take hydrogen electrode on one side and the copper electrode on the, suppose I want to measure copper, so I will take copper on the opposite side. Now what will happen? We know that the difference here we are getting is 0.34 volt. What's the formula for here? E right minus E left. I have E right minus E left, and I know that E left is 0. So I will put here E left is 0. Okay, so the value here E left is 0, right, and E naught value I am getting 0.34. So the reduction potential of copper is what? The reduction potential of copper is 0.34 volt. Now if I want to write it, the cell I want to write it. So this one, this hydrogen electrode is represented like this, platinum H2 H plus. So you can see here I have this one, right? We have, see, this is a platinum wire. On this surface we have H2 gas, and this H2 gas is in contact with H plus. So what we write it? How do we represent this cell? So we have platinum H2 H plus. Okay, then we have this side salt bridge. So you have the salt bridge there. Next, this side what you have? This side you have copper 2 plus, then you have copper rod, right? So that is why this is the cell notation, and you have copper 2 plus 2 electrons gives you copper, and its electrode potential is 0.34 volt. So we got the electrode potential of copper. Similarly, I can also calculate the electrode potential of zinc. Okay, I will put hydrogen electrode on one side and zinc electrode on the opposite side. When I calculate this, I will get minus 0.76 volt. Okay, now what we have understood here, one value you can see that the copper value is positive 0.34, and we have, so this is oxidation potential, this is reduction potential, right, on the right hand side, and the reduction potential of zinc is minus 0.76 volt. So what we can indicate here, what are the learnings we can take from here? Now whenever the reduction potential is positive, that means that species wants to undergo reduction. If the reduction potential is negative, then the species does not want to undergo reduction, it wants to undergo oxidation. So that is why, since zinc reduction potential is negative, so that is why it undergoes oxidation, and it is taken on the left hand side where it undergoes oxidation. So here are some conclusions that you should be knowing, that copper value has a positive value, right? Copper 2 plus is a positive value. So that means what? Cu2 plus ions are reduced more readily than H plus. So if I have copper 2 plus and I have H plus, so there is a, suppose a race, you have copper 2 plus and you have H plus. Reduction potential here is 0, here is 0.34. So there is one electron. What is reduction? Reduction is gain of electrons. So who will gain the electron better? Because it is having higher reduction potential, it will gain this electron faster and will get reduced to copper, right? So copper ions are reduced more easily than H plus, right? So if copper ions are undergoing reduction, right, the H plus cannot oxidize copper metal under standard condition. So that means what? If H plus would have undergone reduction, if H plus would have undergone reduction, it would have an oxidizing agent, right? The species which undergo reduction behaves as an oxidizing agent. So if H plus would have undergone reduction, if H plus would have undergone reduction, it would have behaved as an oxidizing agent and it would have been able to oxidize copper 2 plus. It would have been able to oxidize copper 2 plus. But since copper is undergoing reduction or copper 2 plus is undergoing reduction, it is behaving as an oxidizing agent. H plus cannot oxidize copper 2 plus. Okay. Next, so copper, so if you have generally, you know this reaction, metals react with acids to give you salt plus H2 gas. So let us talk about this here. We have this reaction, metals react with HCl to give you salt plus H2 gas, right? From where this H2 gas is coming, this H plus here is getting reduced. So metal should undergo oxidation and H plus will undergo reduction. But if this metal is copper, then H plus cannot undergo reduction because copper will undergo reduction, and in that case no hydrogen gas is evolved. Okay, so copper does not dissolve in non-oxidizing agents like HCl, and hydrogen gas cannot be produced, cannot reduce H2 either. Okay, so hydrogen gas is not produced in that case. But if you take nitric acid, okay, if you take instead of HCl you take nitric acid, in that the nitrate ion, okay, this nitrate ion is a very strong oxidizing agent, okay, and that can convert copper to copper 2 plus. Okay, but in normal HCl you will not get hydrogen gas. Similarly, if you see zinc, zinc is having a negative electrode potential. That means what? If Zn and metal is taken, okay, Zn and this one is taken, Zn is having oxidation potential, then H plus will have more reduction potential. So what I am getting here, Zn, let me write here. One second. Yeah, so Zn oxidation potential, reduction potential is minus 0.76 and hydrogen reduction potential is 0. Okay, and I have an electron here. So definitely hydrogen will undergo reduction, Zn will not undergo reduction. So if hydrogen will undergo reduction, it will behave as an oxidizing agent, right? So Zn will undergo oxidation there and hydrogen gas will be produced there because hydrogen is undergoing reduction. Okay, hydrogen is undergoing reduction here, so it will be H2 produced, H2 gas will be produced. I hope you are getting this one. If not, let me just try once again to explain this one. Just a minute. So let me just try to talk once again here. Okay, so we have, just imagine you have here, sorry, yeah, here you have copper 2 plus and H plus, okay, and we have electron. Copper reduction potential is more, so it will undergo reduction. H plus will not undergo reduction. When H plus will undergo reduction, then only H2 gas will form. But here copper 2 plus will undergo reduction, so that is why H2 gas will not form. But if we talk about zinc, okay, so zinc has a reduction potential of minus 0.74 volt and hydrogen has a reduction potential of 0 volt. Right? So now if here one electron comes, then who will undergo reduction easily? Hydrogen will undergo reduction. When hydrogen undergo reduction, here hydrogen gas will be produced, here hydrogen gas will not be produced. Okay, fine. Next, so now we have seen that Zn electrode potential I have calculated. How much Zn electrode potential came out? That is minus 0.74 or 76, and copper came out to be plus 0.34. Right, so this is on the right side, this is on the left side. So if I want to now consider a Daniell cell, okay, and if I see Daniell cell left, right minus left, if I do 0.034 minus of minus 0.76, you will get 1.1 volt here. In the starting of the galvanic cell, I told that in this the potential difference generated is 1.1 volt. That is because in the zinc the potential there is minus 0.76 and here it is plus 0.34, plus 0.34 minus 0.76 gives you 1.1 volt. Okay, this calculation don't have to remember, just for explanation. Fine. Now last topic we have, that is your inert electrodes. So what are inert electrodes? So these are the electrodes that do not participate in the reaction. Okay, they do not participate in the reaction but provide their surface for oxidation or reduction reactions. If you see the platinum electrode we have seen, right, here what happens, hydrogen gets absorbed, reaction takes place, but platinum itself is not involved in the reaction. Hydrogen gas is involved, but on the surface of the platinum. So those type of electrodes where the surface is only for the process of oxidation and reduction, but the electrodes do not participate directly, are called as inert electrodes. And example we have here is platinum and gold. You can see hydrogen electrode with platinum, you can see platinum with bromine also. So there are variety of examples here. So students, that's all in today's class, where we have learned about galvanic cell, what is electrode potential, what is standard hydrogen electrode, and how to calculate the cell EMF. Okay, I want all of you to revise this once again, go through the notes. I'll be uploading it. You'll be getting it in the WhatsApp channel, so please do join the WhatsApp channel. Link is there in the description section. And if you have understood everything, then just put a thumbs up or just give me in the comment section that I have understood everything. And if you have doubt in anything, that also you can comment. And how was the session? Did you like? Did you enjoy learning these concepts? Is there anything that can be done for improvement? Your feedback is also welcomed. So please put that in the comment section. Thank you for watching. All the very best, and do not forget to subscribe the channel.